Hello everyone. Today, we will learn about making a capacitive touch sensor on a PCB with Arduino and FDC1004 sensor IC. This is the part 2 of the capacitive touch series. In part 1, we learned the basic principles of capacitive touch sensor through a simple experiment with a single resistor for the touch sensor. Click the link above if you find it interesting. A touch sensor on a PCB is formed with an electrode and overlay, a thin layer of insulator material. The electrode represents one plate of a capacitor. This electrode may have parasitic capacitance due to the surrounding environment, such as the ground plane, which is indicated here as C0. When we make a contact to this electrode, with a finger, it contributes to the capacitance of the electrode. This capacitance change can be detected by using a capacitive sensor IC, such as FDC1004. FDC1004 communicates with I2C with the host. Let me briefly introduce the FDC1004 IC. This is a 4-channel capacitance to digital converter, with a full-scale range of 0 to 15 pF. We can also compensate the capacitance resulting from the circuitry connected to these channels, or from parasitic capacitance from the PCB layout, through CapDAC, having a range of 0 to 96.875 pF, and a resolution of 3.125 pF. You can use all 4 channels for measuring the capacitance, which is called single-ended measurement mode, and also use differential measurement mode for measuring the relative capacitance between channels. One of the great features this IC has, are these shield pins. These pins prevent the measurement to be affected by the environment, such as EMI, temperature, and also the parasitic capacitance. Now let's see how to design the sensor and shield on a PCB for FDC1004. These are several examples for designing the sensor and the shield. All of these examples are showing that you need to place the sensor on the top layer, and place the shield on the layer underneath the sensor layer. This example also shows different size and configuration of the shield. The rightmost configuration is capable of blocking the interference more effectively, with the cost of sensitivity decrease. This reduction in sensitivity can be crucial for proximity sensor designs, but any of these designs are applicable for touchpad applications. Any shape of the touch sensor electrode can be implemented, such as rectangle, round, triangle and others. The size, however, is recommended to be 10 to 15 mm on one side of the sensor. If it is too small, the sensitivity will decrease, and if it is too large, noise susceptibility would increase. Now let's see how to design the sensor on a PCB. The schematic is designed with EasyEDA. The first step is to place the FDC1004 IC, and add optional RC filters on each pins of the channel. These RC filters are intended for reducing EMI above 50 kHz, and these capacitors will add up to the measured capacitance, so it should be compensated with CapDAC. The RC filters are not mandatory, and in my case, worked equally well without these RC filters. And that's it for the schematics. Leave these pins open, and we'll connect it to the electrode when we design the PCB. This is the final product including the schematic we've seen in the previous slide. We have 4 buttons, connected to each channel, rectangular shape on the top layer. The shield plate resides on the first inner layer, just beneath the top layer, having slightly bigger dimension than the buttons. Now, I would like to show you how to make these buttons and connect it to the FDC1004 IC.
This is the schematic we have previously seen. Now click Design, Convert Schematic to PCB, and click No Keep Going, since we know there are unconnected nets. We will select 4 layers, but you can select 2 layers if you want. Let's place the sensor related components, which is U3 here, inside the PCB area. And the RC filter, R4, C28, 26, and rest of the resistors. I'll rotate and place these components real quickly and connect it to the pins. Now to place the sensor electrode, I will use a rectangle from the PCB tools. and draw a rectangle in the empty space below, and set the dimension to 10 by 10. And copy 3 more of these rectangles for each channel. Align it and adjust the location. That's it. Currently, these rectangles are just copper pads, so in order to connect it to the resistor pads, we need to name them the corresponding net name of the resistor pad. If we click the bottom pad of the resistor, and from the pad property, the net name is R4_2. Copy it, click the touchpad we want to connect it to, and from the property, select net and paste. Now you can see that the blue line is added from the resistor pad to the touchpad. Let's do the same thing to the other 3 pads. Copy and paste. That's it. Now let's draw the wire to connect the 2 pads with a wire tool. Try to make the length of each wire equal for the parasitic capacitance to be similar. I'm going to play this a little bit faster. Okay, the top layer sensor pad and trace is complete. Now we need to draw the shield underneath the top layer, which should be inner 1 layer. Add a via to connect it to the inner 1 layer. Modify the width of the trace to 0.5 mm to draw the shield trace wider than the sensor trace. Of course, you can cover the whole area with the shield plane if you have enough space available. Let's speed up a little. Now, I will add a rectangle for the shield underneath the sensor pads. You can see that the net name of this pad is empty, so we need to write the corresponding net name to the property of this box, which is U3_1. Okay, now we made a touchpad with a shield on a PCB. Finally, to label these touchpads, we can add an image. Click Image from the PCB tools, select Image File, adjust the size to fit in the touchpad. There we go. Let's add one more image to the button, in this case a circle. Adjust the size and place it nicely in the middle. Here. Now we have finished the PCB design for the touch sensor. Easy as pie.
Now for the last part, I would like to show you program and use this touchpad in an Arduino environment.
First, we need to install the library for the FDC1004 IC. Click Tools, Manage Library, and type FDC1004, enter. Among the 2 results, I installed the library from Proto Central, and then open the example file. There is one example file from this library, FDC1004 stream. I will modify the code a little bit to print in a new line. This example continuously reads and prints the capacitance of channel 1, which in this library indicated as 0. However, the I2C address of FDC1004 is fixed as 50 in hexadecimal. Let's upload and see what happens. After uploading, the capacitance value read from channel 1 is 74 picofarads. If we press the up button, which is channel 1, you can see the capacitance rises up to 108 picofarads. This example is automatically adjusting the CapDAC offset when the capacitance value exceeds +8 or -8 picofarads. I made a modification to this code to read all 4 channels and print the results. I simply duplicated the code for each sensors. I also added some prints for checking the current CapDAC offset for each channel. After uploading, you can see the CapDAC value is increasing to 22 or 23 to compensate the offset created mainly by the capacitor from the RC filter. By pressing each touchpad, you can see the capacitance value changing accordingly. Great! One last thing I would like to show you is repeat measurement mode. In the previous examples, the code repeatedly enabled a single measurement mode for each channel, which could be better for saving power, but rather slow in terms of response time. In the repeat measurement mode, you only need to configure the measurement once, and the FDC1004 automatically triggers the measurement and stores the result in the register of FDC1004. However, this needs modification in the library. Upload is complete. This code calibrates the offset capacitance during initial stage. So the capacitance value shown here is the capacitance with offset removed. All channels are responding. One last thing to note is you need to add a code for resetting the device before configuring, or else the measurement can be shifted by one channel, which is clearly not an expected behavior.
This is it. Thank you for watching. See you in the next video.